Okay, so welcome back everybody to second day of Bath-Beijing-Paris meeting. So we are very happy to have Lisa Hartung, who will talk about quantitative estimates on the extreme level sets of the two-dimensional Gaussian free field. And I'm going to put in the chat the link to the Google Drive folder where you find all of the slides of all the talks and also the post-session contributions. All right, thanks Lisa for coming.
Okay, thank you very much for the nice introduction. So what I'm going to talk about today is actually is a joint work that we're still writing up together with Maximal, who has just moved from Bonn to Haifa, and Oren Luidor, who already is in Haifa. And what I'm going to talk about is related to Leonid's talk yesterday. So he was talking about estimates on the extreme level sets of branching Brownian motion, and we are going to look in this talk on estimates of the extreme level sets of the two-dimensional discrete Gaussian field. So what is the two-dimensional discrete Gaussian free field? So we think of it as a square box of a certain size intersected with Z2. And for convenience, I'm going to scale the size of the box on an exponential scale. So it has size e to the n. So the box has width length e to the n, and then we intersect it with Z2. And then for us, the discrete Gaussian free field is nothing else but a mean zero Gaussian process on this box, where the covariance function is exactly given by the Green's function of the simple Van der Waals. And this is a well-studied object. And what connects it to branching Brownian motion is that this model also falls into the class of log correlated fields. So the correlations in this model decay logarithmically with the distance of the two vertices x and y. And so what is known about the extreme values of this process? So first of all, one can ask the question, so we have this box as a part of Z2, we can ask, what is the size of the maximum of the field in this box? And it turns out that when we take a box of this exponential size, then the order of the maximum is given by 2 square root of 2 over pi times n minus 3/4 times the square root of 2 over pi log n. And so this you can compute. And what is very characteristic for log correlated fields in general is this appearance of 3 over there. So in Leonid's talk, we also had that there's some linear growth term, and then there's logarithmic correction. And then there also was a 3 appearing, and it's actually the very same 3 as in branching Brownian motion. And what one can show is that if you look at this field on this box Vn and you subtract this order of the maximum, then this converges in law to a limit. This goes back to work by Bramson-Zeitouni and Bramson-Zeitouni. And one can also describe the limiting, the limit more precisely, but I will not really go into that because our focus in this talk will be slightly different. Namely, what we want to really look at is somehow the set of all points that are really high. And what is somehow a key ingredient to understand this is the extremal process. So we look at the whole field in this box and we subtract from the value of each point the order of the maximum. And we ask, can we describe this point process? And as it turns out, you can describe this point process. So this was done by this group and Oren Luidor. You can describe this process, and what you obtain is a decorated crossing point process. And instead of giving you too many formulas, let me explain it to you in a picture. So what you have is there are a few very high mountains where the field is of order of the maximum. And these few high mountains have a peak. And to these peaks, which are the red dots in this picture, we refer to as extreme local maxima. And these peaks of the mountains are then surrounded by the rest of the mountains, namely by neighborhoods where the field is very high as well. And the number of extreme local maxima can be described by a Poisson point process, where the intensity measure is random, namely it contains something that's Z that really corresponds to the derivative martingale we saw in Leonid's talk. And for the two-dimensional discrete Gaussian free field, it's actually the critical Liouville quantum gravity measure. And then there's also an intensity coming from how many points there are, which is like the non-random part. Namely, that tells us that if we go to minus infinity, we see more and more. So if we look at levels, so if we look at levels that are a lot below the order of the maximum, then we're going to start more and more points. And this is somehow indicated by this e to the minus 2 over square root g h term. And then the neighborhoods of these extreme local maxima, so of these Poisson points, well, you can describe them and they are all IID copies of the same object. But for us, it's somehow only important here that you can describe them. And so what we are after in this project is we really want to understand the number of points that are above, or we want to really understand the number of points where the field is above a certain threshold, namely above the order of the maximum minus a large constant. And we want to understand this asymptotic behavior when we first take n to infinity, and then we take t to infinity. And what is somehow the idea? Well, as we take n large, we move to this picture of high mountains with peaks. And as we then make the t large, this number of red dots, so the number of extreme local maxima is going to grow in t. And so what we are going to have to count in this level set are more and more copies of these blue areas, right? So somehow the leading question will be, so if we look at the number of points contributing to the level sets, will it be dominated by just the higher number of extreme local maxima, so more red points, or by sampling more copies of these blue areas? Are we going to see that the level set is dominated by an unusually large copy of this process? Right. And okay, so and as it turns out, so this is statement of the theorem. If we look at this number, right, and we rescale it by some constant times the total mass of the Liouville quantum gravity measure times t e to the 2 over square root g t, then this converges to 1 in probability when we take first n to infinity and then t to infinity. And this growth term here, t times e to the 2 square root 2 e to the 2 over square root gt, it really has the same form as in Leonid's talk for branching Brownian motion. And so what can we see from this? So if we would only look at the number of extreme local maxima, so just at the red points, we would roughly see e to the 2 over square root g times t many. because that is somehow the second part of this Poisson point intensity I was telling you about earlier. So the fact that there's an extra term in the growth of this in this theorem tells us that actually the clusters, so these blue areas, contribute significantly more to this level set than just the extreme local maxima. And okay, the analogous theorem, we proved it with Azer and Oren a few years ago for branching Brownian motion. And then there's this more recent work that Leonid was talking about yesterday, where they actually refined the estimates. So this theorem somehow builds a lot on the methods we use for branching Brownian motion, because they are probabilistic methods, so they are more well suited to be adapted to other log correlated fields, whereas this work Leonid was talking about, it relied purely on this FKBP equation. So it would be really hard to work with this here. And so the picture that somehow stands behind this theorem that you should keep in mind is somehow there are a few very big clusters, so blue areas, that really carry most of the points of this level set. And as I already said, we're going to try to really use that branching Brownian motion in this discrete Gaussian free field are very similar, at least when you use methods such as first and second moment method. Before telling you a little bit about how we do this, I want to tell you another kind of interesting story about these level sets. Namely, what you can think about is, so you have this, you now believe that if you pick uniformly at random, let's say, a point of this level set you're looking at, right? That you pick something that's not an extreme local maxima, but it's something that belongs to one of these blue mountains, and it's somewhere. And now you can ask yourself, can you say something about its relationship to the extreme local maxima it belongs to, right? So you pick a point uniformly at random from the level set, it sits somewhere, it belongs to a mountain. And now you can ask yourself, you know, what is the distribution? So now you can look from there to the peak, and you can ask yourself, how do these points depend on each other, right? And there are somehow two questions you can ask. First of all, there's a height difference, right? Because the point that you've picked should be lower than your peak. And then you can also ask a question about the spatial distance of the two. So these mountains, they have size order 1, they are really around this peak. But the question is, can we actually understand more about this? And the answer is yes, if we scale everything in a good way. So we take a uniform point from the level set. We take y to be the peak of the mountain x belongs to. And then if we scale the logarithm of the distance of the 2 points by t squared times g, but this g is just some constant in the first component, and then in the second component, we look at the height difference divided by t. Then this converges to some object in distribution, where this object it converges to is that the time and the value of the global minimum of the Bessel-free process that we start from 1. Right, so this limiting picture on the right-hand side that we would like to find, well, somehow the picture is this. So somewhere there's a hidden Bessel-free process that is conditioned. So it's just, you know, some Gaussian process starts at 1 condition to not go below 0. So at some point it will take its lowest value. And at this point where it takes its lowest value, it also has a certain height. So this height actually turns out to be uniformly distributed. And you can also say something about this time. Right? So so this scale, so that this is uniformly between 0 and 1. Well, that's maybe not too clear where it comes from, but it's that it's something between 0 and 1 makes sense, right? Because we pick a point above minus t, and the highest point should be roughly, the highest peak that we could see is close to 0. So somehow there we have a range from minus t to 0, and if we divide it by t, we go from 1 to 0, right? So this explains this axis. And then the other axis here, it just means that there's some kind of diffusive scaling with this t square. That I will explain where this t square comes from in a second. Okay. And of course, you can also ask a similar question in branching Brownian motion, but there we only looked at this first component somehow, and not at the spatial component. Okay, so let me try to explain to you a little bit where all these things come from and why we see them appear. So what you can do is essentially you can try to make, so you take your field around this extreme local maximum, and now you try to mimic a Gaussian branching random walk. And the way you're going to mimic it is that you take this point and then you decompose your field into annuli around this point, and to reflect somehow the covariance structure, you make these things, the distance between the boundaries, grow exponentially. So you take these boxes of size e to the L, and then you take out e to the L minus 1, right? So this just means that somehow each branching random walk increment should roughly get variance 1, right? And now, of course, instead of count all the points in the field that are high, you can also count all the points in these annuli that are high. And in each of these annuli, somehow you have a restriction that your field should be less than the value that you have at this extreme local maximum, right? Because you say it's the peak of the mountain, and you could say, well, this means that it's the highest point everywhere. So this means that this somehow adds an extra constraint, and this is somehow going to play the role of a localization of path, right? So we somehow say, okay, no, so we have a fake branching, we have a fake path, and this fake path also has a fake constraint to fulfill, and this comes from the fact that the field needs to be equal than the field value as the 6 kilograms. Okay? And now we're going to think, this can be made more precise, but we're going to think about each of these boxes as one increment somehow of a Gaussian branching random, a Gaussian random walk. So each AL somehow represents one increment. And then somehow what we see is intuitively, right? Very intuitively, is that what you see is actually something like a Gaussian random walk that is conditioned to stay negative. Right? So this staying negative comes from the fact that your field in all the annuli should be smaller than the field in the middle where it's the highest. And then all the increments that are represented by this field in the annuli, they are the Gaussian random walk. And this is an object you can understand much better, right? And where you know how to do a lot of probabilities from. And to make this turnaround very precisely, we use valid estimates for the two-dimensional discrete field, which were established in a separate article by Stefan Gufler and Oren Louis-Dor, and this is something very technical, but it can be done, and essentially it means that you make this whole turning the annuli into branching random walks as precise as you want. So now, right? So now on a logarithmic scale, we have turned everything into understanding somehow a Gaussian random walk to be below 0. And what we observe is, if we now turn this back into how many points are there, is that the main contribution to our level sets come from mountains where the field at distance ut squared, right? So we are still on the logarithmic scale. Right? So this is everything. So in this picture, we are on the log scale. Comes from a region where the field at distance ut squared is high. Right? So instead of being repulsed and going away from zero, this is when the walk comes close to zero and then goes down again. Right? And so what we really need to establish really well is the number of points that such an event would then contribute to the level set. Right? So I pay a certain price to go close to zero at this time point, but then I have a lot more that I'm going to contribute, right? So there's a trade-off between how unlikely it is somehow to observe this versus how many points can I give to the level set if I do this unlikely event. And for this we need asymptotics. And how does this? So this we do with first and second moment estimates. But how does this relate to this Bessel process picture I was telling you about? Well, so this point where this ut squared comes from, where you contribute most, well, this is exactly what gives this t square scaling here, right? So these points here are then exactly the annuli that contribute most to the level set. And since they contribute most, I'm most likely to observe them if I randomly pick them. And that it's a Bessel process comes from the fact, well, that I have this somehow the starting point that I choose, I mean, the mountain that I choose is somehow of order 1. And then my actual constraint, well, there's a little bit of difference, but then I have this constraint, right, that this other point is also above minus t, right? So this is somehow the overall condition that the field has to not be too high. Right? It's always a question how you flip this picture. So this condition becomes this, and this is you rescaled everything so that your Gaussian walk really looks like, some continuous object. So it's not so surprising that you get such a thing. And well, and this is the height difference, right? And where does it come from? Well, you have this random walk that has this conditioning, and you're most likely to be an offspring from the point where you come the closest to the barrier. Because if you're the closest to the barrier, somehow you get most of the offsprings. So so you're most likely to pick a y that comes from the point where you could make the field as high as possible. And this actually means to come as close to the barrier as possible. And this coming close to the barrier point is exactly this minimum of the Bessel point. And at this time, it happens at a certain random time, and it happens at a certain random height. And this is exactly what you observe in this picture. And I will stop there. Thank you very much.
All right, thank you, Lisa. Are there any questions for Lisa?
Looks like Julian and Christina both put their hands up.
Okay. So, Julien?
Actually, this was clapping, but
I was clapping. Sorry.
But
my Zoom skills are telling me.
Can I ask just one very naive thing? So, can you just re-explain briefly? I always get confused by the how you see the field as a genealogical picture. Can you remind me how that works? Right. So you're saying, the particle is a descendant of this of mass coming from that position or something like that, but what you have is a field.
So what do you mean about the? So you mean about the distance? So
Yeah.
I mean, yeah. I mean, here distance is somehow easier, right? Because right? Because I mean, somehow for us, distance really is somehow. So if you, right, it's somehow really. So distance here really is the Euclidean distance, right?
Mm.
And if you want to map it somehow to this BBM, you have to take the logarithm of it.
Okay.
Right? Because this has to do with somehow how much variance you lose, right? Because you lose only on a logarithm. I mean, if you go away somehow, right, you always need to go further away somehow to find points. Because, right, so somehow you find all points that have, you know, that have covariance kind of 1 with this red point, and then you go to points that have, you know, covariance 2, variance 3, and this you have to do because you are, and this you have to do on a logarithmic scale because this Green's function is logarithmic.
Yeah, yeah.
Right, so that's why you have to choose these boxes of somehow of, so these boxes are somehow of size e to the L. So these annuli are e to the L, and then each of these annuli somehow really represent one step in a branching when a walk, but you start, but somehow on this exponential scale.
Okay. Yeah, and I have one more question, maybe if I have time. So you also said the analog, you mentioned very fast at some point that there will be an analog result for the BBM, which would be this uniform distribution?
Yes.
Can you just explicit that a little bit more?
So yes, so maybe go. Let me maybe go to this theorem.
Yeah.
Okay. So here.
Yeah, exactly.
So what you can do is you can, so for BBM, what you can do is you pick x as here, and then also y is now also the argmax, but of the but now the neighborhood is the neighborhood in this tree, right? And then you can look at the height difference of x of y and x, right?
I see.
And divided by t, and this is going to be uniformly distributed.
Okay.
This has to do with the fact that if you look at, so if you look at a Brownian bridge, right, but just around 0, and you know you wanted to, and now you ask what's the probability, and you say stay below 0, and you ask the probability, what is the chance that it actually has distance delta, right? So if you have this Brownian bridge type of things, right, and you actually ask it, and of course around 0 you leave a little bit of space. Instead you ask it to be below minus some delta. Then somehow the probability that this object fulfills also the wet constraint towards not fulfilling it, it's actually linear in this distance delta. When you linearize, so it's actually really linear in this distance delta.
Okay. Okay.
Right, and somehow it just means that if you look at this Brownian object that's conditioned to stay positive, right, it will at some point be the closest they have in this neighborhood, be, you know, close the proper, somehow if it becomes close on a certain scale to this barrier, you lose 1 over the distance where you do it in terms of probability. But if you condition on it, on observing it, this is exactly this point is exactly uniformly distributed somehow.
Okay, thanks.
Yeah.
So Pascal, you're muted. I'm not sure if you're trying to talk, but we had Zheniao raising his hand, and there's a question in the chat, but we might have to move on and save those questions for the discussion because I don't know what you think.
Okay. All right. Okay, so then let's thank Lisa again, and by clapping, so you're free to unmute yourself and clap. All right, and the next speaker is Roman Stasinski, or Romek. Are you able to share your screen, Romek?
Yes, so first of all, can you hear me well?
Yes.
Okay, perfect. Okay, so I guess that my screen should be now visible.
Yes, it is.
Right, great. Okay. So, ready?
Yes, already.
Cheers. So, hello everyone. I'm going to talk about work that was done during my PhD studies at the University of Oxford, where in collaboration with Julian and Bastien Malin, we tried to understand what could be said about the faraway particles of the multidimensional branching Brownian motion. So let's start with a very brief recap on what a branching Brownian motion dimension 1 actually is. It's a process which starts with one particle located at some position x, and this particle starts moving according to the standard Brownian motion. And independently of the movement, it starts branching at rate 1. And finally, at each branching event, it splits into two particles, which from now on continue the same movement independent from each other. So as the time passes, we get a growing cloud of particles with size actually growing exponentially. A bit of notation, by calligraphic NT, we're going to denote the set of particles that are alive at time t. And by capital X t of j, we're going to denote the position of the particle j at time t. This talk is going to consist of 3 parts. In part 1, we're going to talk about the known results from the one-dimensional setting. Then we're going to move to the d-dimensional setting. We're going to state some results and conjectures. And the final bit is going to be devoted to the very quick run through the proof of our main theorem. So what is actually known about the external particles of the branching Brownian motion in dimension 1? It was proved by Brownian in the late 70s that the expected position of the furthest particle is square root of t minus a logarithmic correction. So Brownian actually proved that if you look at the position of the maximal particle, if you normalize it by nt given above, then this object is going to converge in distribution. The next question we might ask is, okay, so what can we say about the fluctuations about the expected position nt? And Lally and Selke stated the following question. Imagine that you observe your process until time s being pretty large, and then based on that, what can you say about the fluctuations or about the relative position of the maximal particle at time t much larger than s with respect to the expected position nt? And they found out that this relative movement with respect to nt can be attributed to 2 factors. First of all, we're going to see fluctuations which are going to follow the Gumbel random variable, the distribution of the Gumbel random variable. And also we're going to see a random shift that is given by a logarithm of a limit of a process zt called commonly derivative martingale. Before we state what the derivative martingale actually is, let's just get some intuition about where this shift might come from. So thinking about the initial stage of the process, like imagine that with some probability, your first particle could shift to the left by a significant amount, or it could shift to the right by a significant amount. In both cases, this introduces a lag, which is propagated in time. And that's actually the random shift that we recover when you look at the relative position of the maximal particle with respect to mt. So what exactly is the derivative martingale? It's easier to first introduce the additive martingale, which also plays an important role in the branching Brownian motion literature, because now when we compare the two, we see that both are given by a sum over all the particles that are alive at time t of some function of the position of a particular particle. And if you look at the function that is used in the definition of Wt, then it turns out that the function used in the definition of Zt is the rescaled derivative of the previous function. So in case of Wt, it's pretty easy to see that this is a martingale and that it converges almost slowly because the contribution of each particle is always non-negative or strictly positive. But in case of the derivative martingale, well, one can easily check that this is still a martingale, but each particle can actually have either negative or positive contribution. And in particular, particles that travel very far away, so above square root of t, have a very negative contribution to the sun. Nevertheless, it was proved by Neville and Lally and Selke in the late 80s that the limit of ZT actually exists, and it is almost truly finite. Okay, equipped with that knowledge about the relative displacement of the maximal position with respect to expected position, we asked the following question. What could we actually say about the joint distribution of the leftmost and the rightmost particle in this setting? The first observation is that if you look at the leftmost particle, then we could actually flip the sign of all the particles of our BBM, and then what we call the leftmost particle now becomes the rightmost particle of the new BBM. So this gives us a way of defining a derivative martingale that corresponds to the leftmost particle. So now we have two derivative martingales, one being the standard one that corresponds to the rightmost particle, and one that corresponds to the leftmost particle. And we ask a similar question to the one that was asked by Lally and Selke. So consider, like, imagine that your process runs until some large time s, you see your cloud of particles, and then based on that knowledge, you try to predict what is the probability that at time t much larger than s, the rightmost particle is going to be further away from zero than the leftmost particle. And it turns out that if we take an analogous double limit, so first t going to infinity and then s going to infinity, we're going to recover a distribution which can be given by two numbers. And these numbers are normalized derivative martingale corresponding to the rightmost particle and derivative martingale corresponding to the leftmost particle. And the intuition behind this result is as follows. We know from Lally and Selke's results that if we look at each of these two particles separately, we're going to see Gumbel fluctuations with some shift. Furthermore, with high probability, we can check that the particle that is rightmost and the particle that is leftmost, they must have split very early on. Therefore, those Gumbel fluctuations should be more or less independent. And finally, it's an easy calculation that if you take two Gumbel random variables, which are independent, if you shift the first one by log A, if you shift the second one by log B, and if you look at the probability that the first term is larger than the latter, then you basically obtain A over A plus B. And that's what we got in our result. Okay, we're now ready to move to the d-dimensional setting. So first of all, what do I mean by the d-dimensional branching Brownian motion? It's exactly the same process as I described at the beginning. The only difference is now that all the particles move according to a multi-dimensional Brownian motion instead of a one-dimensional Brownian motion. An important observation is that if we project our multi-dimensional branching Brownian motion, or BBM in short, onto any particular direction of the unit sphere, we're back in the one-dimensional setting. So we know quite a lot about this. And what could we say about the position of the furthest particle of this multi-dimensional branching Brownian motion? First of all, well, one can easily see that if we look at the expected position at time t, then this position is going to increase in dimension because we basically add more and more degrees of freedom where the maximal particle can fluctuate. And the actual correction was determined by Bastien-Malin, who proved that again, like when we increase the dimension, we add another logarithmic correction, and this increase is linear in the dimension. So Bastien proved that if you look at the family of distributions corresponding to the position of the furthest particle centered by this term, then this family is tight. And this result was recently strengthened to full convergence distribution by Kim, Lubetzky, and Hartung. Okay, so we remember from the one-dimensional case that the derivative martingale played a significant role in the description of the behavior of the external particles. So we can kind of also guess that this is going to play a role in the description in the multi-dimensional setting. So we're going to define an analog of the derivative martingale as a process on the sphere where basically in each direction of the sphere, we project our multidimensional branch environment motion onto this particular direction, and we calculate the derivative martingale based on this projection. So we end up with a process in the sphere. And we know that if we fix any particle direction theta, then this process, so then zt of theta is going to converge almost surely. But does it mean that the limit exists simultaneously for all or almost all thetas from the unit sphere? The answer to this question is actually yes, and that's what we prove in our main theorem. We show that the derivative martingale, seen as a process on the sphere, so in this multidimensional setting, converges weakly to a random measure. And here by a weak convergence, I mean that if you look at scalar products of our derivative martingale with any bounded and measurable function from the sphere to real numbers, then such scalar products do converge. What is more, this limiting random measure has a density with respect to the Lebesgue measure, and this density is actually given by a pointwise limit of the derivative martingale for almost all thetas. So to put it simply, we proved that the derivative martingale, seen as a process on the sphere, converges to a random integrable function. And why do we actually think that it's interesting and important? So if you remember the one-dimensional result that we talked about like 5 minutes ago, when we looked at the cloud of particle at some large time s, and based on that, we wanted to predict whether the rightmost particle is going to be further away from zero than the leftmost particle, then we claim that something similar holds in the d-dimensional setting. So we conjecture that if you look at similar double limits, so you observe your process until time s, and based on that, we want to predict the distribution. Now we have not only like direction plus or minus, but the distribution of the angle of the maximal particle, then we claim that the limit that we obtain is actually the measure that we obtained in the previous theorem. Okay, I'll leave this conjecture as an easy exercise for the audience. And in the meantime, let's have a look at the proof of our main theorem. So again, let's start with the basics and let's recall how one can usually prove the convergence of the derivative martingale. As you remember, the issue of the derivative martingale was that each particle could have either negative or positive contribution. And in particular, particles that travel too far away, above square root of t, have very, very negative contribution. So how can we remedy this issue? Well, we can just get rid of the problematic particles. And this procedure is commonly known as shaving. How do we do this in practice? Let's define a set NTA by analogy to the set NT defined at the beginning. So basically, this is the set of all the particles that until time t haven't hit the barrier square root to s plus a. So in other words, all the particles that stay below the red line until time t. And by ZTA, we define an analog of the derivative martingale, where we have an additional term a in the bracket, and we sum only over particles that are still alive at time t. So over particles that haven't hit the red line until time t. So one can easily check that ZTA is again a non-negative martingale. Well, it's non-negative because we kill all the particles that would make the contribution, that would have a negative contribution. Secondly, one can also check that the contribution of this additional plus a factor is going to converge to zero almost surely. And the third observation is that we know from Bamson's result that at large times t, all the particles are going to be well below the line square root of t. So the only moment or the only time where they could hit the barrier is at the beginning of their life. And this means that as we start pushing the barrier a higher and higher, the probability that none of the particles ever reach this barrier is going to converge to 1. But this tells us that we can recover the limit of the derivative martingale as a double limit. First, we fix a, so we place our barrier somewhere, and then we look at the limit with t going to infinity of ZTA. And then we push the barrier to infinity. Great. So maybe we can do exactly the same in the d-dimensional setting and just shave the projection of the BBM onto each direction. Well, if you remember Bastion's result, then you see that the issue is that in dimension d greater than 4, we're going to see particles that will be much higher than square root of t. That means that no matter how high we place the barrier A, there will always be particles that hit that barrier in their lifetime. So the conclusion is that we won't be able to recover the limit of the derivative martingale when we let A to infinite. So what could we do what could we do now? Well, the next idea is to maybe use an increasing barrier. So let's take phi that grows fast enough and just replace A and the previous definitions by phi. So now we kill particles as soon as they reach the line square root of t plus phi. And well, it looks great, but the problem is that an object defined in, as we did on top is not a martingale. So it's not easy to work with. But it still seems to be a good idea. And it turns out that for a nice function phi, we can actually find another function r of two arguments, x and t, first corresponding to location, the other corresponding to time, such that if we define zt phi in almost the same way as the derivative martingale, the only difference is that we replace the linear term by the function r phi, and we again take the sum only over the particles that haven't been killed until time t. Then it turns out that we can find a function r such that this process, zt phi, is a martingale. And also it is a good approximation of zt for large times t. Okay, so now we are ready to present the main proof, which consists of 5 main points. First of all, we show that zt phi is indeed a non-negative martingale. Then we look at the scalar product of zt phi with any fixed function g. We can assume without loss of generality that function g is positive. So we look at the scalar product and we prove that it is in uniformly integrable martingale. In step 3, we use this fact that this is a uniformly integrable martingale to show that actually we can swap the limit with the integral. So in other words, if we take the limit of a sequence of those uniformly integrable martingales, then this limit can be given as a scalar product of the pointwise limit of z phi with the function g that we fixed. In the next step, we show that the function r is indeed asymptotically linear, which allows us to claim that the zt phi should be close to zt of large times t. And step 5 is again an analog of the last step in the proof of convergence of the derivative martingale in dimension 1. So in other words, we take a sequence of functions, maximal phi in A, and we first take a limit in t of the corresponding shaped derivative martingales, and then we take a limit in A of those limits, and by this way, we recover the limit of the derivative martingale seen as a process of the sphere. So the proof is almost over. There is one step missing, and this is this uniform integrability. So how do we do that? We use we use the martingale of interest to define a new measure Q. And it turns out that under Q, our branching Brownian motion has a very nice description. It can be generated as follows. First, we can pick some direction theta naught according to random variable corresponding to density given by g theta. And then we first generate the branching Brownian motion by determining the behavior of the spine. So we say that the projection of the spine of the branching Brownian motion, spine is one particle line of particles of the BPM. So we say that the projection of the spine onto theta naught is going to be a Brownian motion with a drift square root to t, conditioned to never hit the barrier square root to t plus phi. Then we say that the movement of the spine in the orthogonal space to theta naught is just a standard Brownian motion. Furthermore, the spine branches at a doubled rate, and as soon as particle branches off the spine, it's going to behave as a standard branching Brownian motion. Okay. So with this description, we use a standard dichotomy argument. Instead of proving that our martingale of interest is actually uniformly integrable under P, we show that this martingale, the same martingale, is almost truly finite under Q. Okay, so the conclusion is that we proved that the Dirac martingale, seen as a process on the sphere, converges almost surely to a random integrable function. And the next step would be to prove the full convergence of the branching Brownian motion in dimension D to the external, the full convergence of the external point process of the branching Brownian motion. Thank you very much.
All right, thank you so much, Romek. I think we have a lot of time now. Are there any questions? So Jenny,
I have a question.
Yes, please go ahead.
Yeah, I just want to make sure I understand the notation right. I think it's on your page 5 or 6. I don't know. Can you get there? Thank you. Oh yeah, here. So I just want to make sure that, because I saw the particle has been chosen in nt plus s, but the position has been compared at time t, the xtg. I just want to make sure it's what I understand, that you are choosing somehow particles at the time t plus s, but you're comparing them at like a historical position. Is that what I mean?
I think that it could be understood in a slightly easier way, because basically, like, if you fix s, then we basically look at the particles at some time t plus s, or we could just forget about s and just look at particles at time s, and we look at the probability condition on the information that we have at time s.
Okay.
So we don't compare with anything historical. We just condition on what we see until time s, and from that moment on we look forward and let the time go. Does it answer your question?
Okay, I just want to make sure I understand this notation right. Also, I also have another question about your conjecture there. Later, I noticed that in your conjecture, the left-hand side is like a deterministic, but on the right-hand side, it's like a random object. So I was wondering, maybe there's some details to this conjecture that this is not exactly what you're trying to show, but maybe by some conditioning, I don't know.
Yes, that's what I meant by saying that we want to formulate, like, we want to consider a double limit. So as in the Lally-Selke result, or as in the result that we just described on the slide 6, we first condition on what we see at time s, and then we let time t go to infinity, and then we take s to infinity. So again, this is just a simplification of the theorem that could be formulated using a double limit.
Okay, thank you. That's all.
Thank you very much.
Okay, is there any other question? So I have one. Matt, you also have one, right?
I also have one, but go ahead.
Okay. Yes. Well, since we're on the right slide, yeah, I'm a bit troubled by this conjecture. I mean, there is this additional Gumbel noise, right? That's added. So how come this doesn't play a role here in this conjecture? Well, okay, it's a okay. It does in okay. Now I understand. Actually, it does in the same way as it does before, right?
Yeah.
Okay. Yes. Okay.
So you've answered your question.
Yes. Stupid me. Okay.
So
but relatedly, could you explain again? So how with this extra Gumbel noise you get to the addition to the different log correction in. This is explained by the Gumbel noise, right? This has nothing to do with here the Z infinity, right?
No. Yeah, exactly.
Right. Well, okay.
I mean, it's just at the moment it's a conjecture here. So clearly, like, when we consider the whole spectrum of thetas, like we cannot argue that, well, we're going to see this form in the limit. But if we just fix the finite number of thetas, so like a finite number of directions, then exactly the same calculation that we did for the one-dimensional case would give you like a sum here instead of an integral. So that's a hand-wavy argument why we expect to see this form in the limit.
So Matt, you had a question, right?
Yeah, just to go back to your one-dimensional theorem. Can you say anything more about the difference between the two, the maximum and the minimum, or the maximum and minus the minimum?
I guess that I'll disappoint you because I haven't actually looked at this, so there's not much I could say.
Okay, fair enough. Any more questions?
Well, I had one more. So I think you can, that there are like obvious generalizations to branching random walks, right? And that you should be able to prove.
Possibly.
Well, of course, it's not isotropic, so things are a bit more difficult, but have you thought about how to get around it?
No, at least me personally, I haven't thought about this. Maybe the other authors. So maybe if you direct the question to Julien or Bastien.
Yeah, well, I haven't thought about this as well. I mean, I guess that, you know, if you take a branching random walk where the displacement support at least, you know, allows you to go into any direction, then the extremal point process in the limit won't look that different once you do the appropriate, you know, scaling. But
I see. So you would transform the convex shape into a ball.
Yes.
Right. Okay.
Yeah, you might have you might get an ellipsoid rather than a sphere. But you know, this is just up to you know, a homothetic a linear transformation of your space. It's going to be the same, I think.
Okay. All right.
Bastien, do you want to say something more, maybe? No. Okay.
All right. So if there are no further questions, then let's thank again Romik for this very nice talk.
Thank you very much for your attention.
And so we get back together down to the coffee break, enjoy the coffee and the cookies, and let's meet again in 15 minutes.